Welcome everybody to that session in which I will give you some insight on our embedding activities on power electronics applications, which is a topic that we focus on quite a long time meanwhile. And just to give a short outline, what I have prepared to you, just to give you these insights. I just give you a quick overview about innovative power module technologies, not just what we are doing, what's the general situation there, and then I would like to dive a little bit deeper into our concepts or the concepts in general, what you need to consider in terms of thermal, electrical in these applications, the semiconductor itself. Just a few words on the materials that we are considering for these approaches. And then I would like to give an insight on the process itself and also give application examples, just to close with also some novel concepts which just do not just focus on the power electronic switching cell itself, but also the driver and logic integration before I would summarize my talk. Okay, just to give an overview or start with the overview. What is the main purpose? What's the goal of that embedding of power semiconductors compared to a traditional wire bonded module? So the basic idea is to bring that structure, like shown here in that sketch, into a planar configuration where you have very short connections with these direct copper connections, which give you mainly two benefits on the first side. One is you will definitely have an improved reliability of your interconnection technologies, and also by get these wire bonds eliminated by these very short connections, you will also significantly improve your electrical performance with these short connections. And this has a huge impact on the reduction of the switching losses and also the parasitic inductance. And what's possible to do here, it's not just single die packages, what we call pre-packages. Also, we look into power modules, which could be simple half-bridge configurations or complete power inverters, or also what I would like to give it as an outlook at the end, complete 3D modular systems there. Just to give you an overview, so this is basically a European look. Not really disclosed what's happening in Asia, but basically for the European, there are 4 main partners or parts that are doing work in this area. The 2 on top here, Schweizer Electronic and AT&S. I've also recognized in the list that Thomas and Mike, you're already in that talk, so you will see a lot of familiar things that I will present in the next minutes. They have the most experience here. They have products running in series, different configurations. I will not go into detail here. Also Unimicron Germany, so the former Ruvel part here in Geldern, works toward that technologies. We've been together with them in different funded projects and also working in industrial projects together with them. And also Würth Electronic does some work, not just for SMD embedding, but also for the bare die embedding, and also have some focus on power electronics. But compared to the other 2 above and also Unimicron, I assume that's not that huge amount that they're doing there. The module which always comes up as kind of a benchmark, which is also quite a real innovative approach, is that so-called MPEG from Semicon or Semicon Danfoss right now, which is not an embedding approach, but it's also reducing significantly the electrical paths. So it's a double sintered approach on a ceramic substrate where you sinter your semiconductor, and then you have a kind of flex substrate, which is sintered also on top. And with that, you pretty much are able to reduce these paths in a similar way, reduce the stray inductance. You can also achieve very low inductance here. And it's also mainly focused on battery electric vehicle applications, and it's also scalable in different voltage and also power classes. What we are doing at Fraunhofer ICM, Eric mentioned that I lead that group embedding and substrates, and we have almost 20 years of experience in power embedding. So we started with that back in 2005 in the first European funded project where power was not that high like now, but it was also the first silicon MOSFET approach that time. What we have here in Berlin is a complete state-of-the-art process line, which pretty much enables us to create prototypes or do feasibility studies based on different technology approaches, like on thick copper PCB, high current PCB, organic or ceramic isolation, and also to address different configurations like single die packages, half bridge modules, driver integration, and all that. And that's also the way how you could work together with us in terms you have a certain approach that you need to realize in these different ways that I already mentioned. Okay, I would like now to jump over more into the details of our approaches, go into the concepts first. What you do see here is mainly the two different ways how to create a high voltage power module. A very important point is always that you need to apply an electrical isolation to your heatsink area, and this could be done in two different ways. Either, like shown here on the left-hand side, using an organic material, which is most fitting into a typical PCB like line arrangement, or if you would like to look into a higher power density, you also need to consider ceramic isolation, like a typical DBC or AMB or DPC substrate. And these two variations are mainly the same. At the end, they are just a little bit different in the way how you produce them, either in a subsequent attach of the ceramic on a suitable substrate and then the silicon carbide or silicon die, or doing the embedding of that ceramic substrate into a core material and using that as your initial base plate or base material, and then do all the assembly and embedding followed by that. If you compare these two approaches, it's quite obvious that this has for sure limitations in terms of the power density, because even if these layers could be thinner with the same breakthrough voltage than the ceramic substrate, with a typical maximum available thermal conductivity at the moment going up to 10, maybe 10 watts per meter Kelvin, you have certain limitations here, whereas with the ceramic materials, you can pretty much aim for higher power densities. If you look into the thermal design, it's very important that you understand what's happening into in your module that you'd like to realize. Also look into modeling these approaches, because if you look into what's happening there, it is the case that for very high power module, one single silicon carbide chip can generate more than 100 watt in heat. That means if you have a configuration like shown here with 10 or above or more than 10 dies for just one half bridge structure, it's very important to pretty much spread the heat, like in that simulated picture here, in a very good way, where you see here not a good spreading, here very good spreading of these heat coming from the dies in the complete copper area, and then have a larger path to bring that efficiently back to the backside of your module, to the heatsink area or the cooler area. Just to give you an idea on the impact of using either an organic insulation or a ceramic insulation, just a simple thermal estimation on both approaches. So the idea or the base here is a similar die with a size of 25 square millimeters, same thickness, with a difference on the organic insulation approach. You use a copper heat spreader, copper lead frame of that size with 2 millimeter thickness, and a thermal conductive, quite low thermal conductive material with 150 micron thickness, and same conditions in terms of the cooling water and the junction temperatures, which brings you at the end to a current per MOSFET of 85 amps that you can switch here. If you compare that same chip but different configuration in terms of the insulator, using an aluminum silicon nitride AMB configuration with half a millimeter of copper, 250 micron thick ceramic, and then the same for the copper on the backside, with a quite high thermal conductivity, you can achieve quite higher current, or you can switch a quite higher current of up to 140 amps per MOSFET, which at the end shows you that using such a ceramic substrate can give you a much higher current density within one chip. With that, you can reduce your silicon carbide amount in the complete converter or inverter structure. However, you need to consider that the ceramic itself would bring you to higher costs in terms of the material, but also for the processing, because this is not that nicely streamlined in the typical PCB world like the ceramic material. From the electrical design, it's typically that you will face something like these inverter structures, which are out of 3 half bridges in a typical B6 configuration, where you have these high and low side switching cells. And if you look into that planar structure in the cross-sectional view, you have your DC plus, your DC minus, and your AC contact. And if you then look into how the electrical current flows here, you do see coming from the DC plus and the DC minus, you have a very short connection length through the switching cell, going to the AC connections. And with these very short DC link loops, you pretty much are able to reduce these inductance to values below 1 nanohenry, which is a significant impact on the complete electrical behavior and the switching losses and everything which is goes together with that. And also, in addition, using that planar structures, having the possibility to use the third dimension, you can already place components which could not be embedded, put them close to the switching cell on the top surface of that module itself. A few words on the semiconductor itself. Typically, you will find silicon carbide MOSFETs at the moment in the area of 25 square millimeters, which a little bit increasing in size at the moment. Typical thickness between 50 and 400, where also here the trend is going, micrometer, where also here the trend is going to thicknesses way below these 400, more in the range 100, 150 micron thickness, typical voltage, typical currents that they can drive. And very important for the technology that we are applying, the embedding, is that you provide the right, or that you have the right metallization of your contact pads, because this needs to be fit into that process technology. That means if we do an approach where we do silver sintering of the component on top of the substrate, you can use the standard silver backside, which is provided with the semiconductor for the sintering process. But to be compatible with the embedding process, you need to provide copper contact pads, which are fully fit into that process chain in terms of the laser drilling process, but also the metallization processes and needed additional processing for that. And this is something that is absolutely a requirement. So you cannot work with that aluminum metallization, which comes standard as a standard with the semiconductor. Okay. The materials that are used for the embedding, if we talk about PCB or laminate-based embedding, are not typical consumer product light laminate materials. So what we need to look here is that we really have a high thermal stability, because if we talk about high junction temperatures up to 175 degrees C or more, these materials need to withstand that. So we look into TG temperatures up to 300 degrees C. Also, the breakdown voltage of these materials is very important, and for sure they also need to be suitable for embedding in terms of the thermomechanical behavior. On the other hand, they still need to be processable within standard PCB equipment. And just as a selection of typical materials that we are looking into here are from Resonac, the former Hitachi Chemicals, also from Panasonic or Risho, which provide kind of these materials. If you look into these thermal conductive materials, which could be a possible replacement of the ceramic substrate if they would fit into the application in terms of the power densities. Again, here also there are several materials available on a market, also from Resonac or Risho or Panasonic, going up to 10 or also 20 watts per meter Kelvin on an R&D status at the moment. And this is something which might be also interesting for certain applications. From the ceramic substrate, since I mentioned that approach, and which is a very important approach, meanwhile, they can provide that high thermal conductivity. Mainly, we do focus here on silicon nitride ceramic substrates because they have proven to be suitable for embedding into laminate material. Typically, you look into bring them down to smaller tiles in order to be compatible with the embedding process. And also, aluminum nitride, for instance, has a almost double thermal conductivity compared to the silicon nitride. This is not really suitable for embedding approaches because of its brittleness. We did do tests on that, but this is not really something which goes, which is really proven for the embedding process itself. I would like now to go over to the process technology, and just to bring that back from the beginning, what's the major goal? So the goal is bring a structure like that, where you have your ceramic substrate brought into kind of these frame modules with the wire bonds into a planar structure with the embedded components, with the short connections, with a routing possibility to bring components on top of that, going away from these strong design limitations and these highly inductive connections to that huge degree of exploration for new design ideas, the improved electrical performance by the short connections to the die. This is a slide I've shown, I don't know, a couple of tens of times. But it basically illustrates the typical embedding approach. So what is done is you have a kind of a PCB processing with the addition of the die attach process and the connections that you need to establish to the embedded component afterwards, after the embedding. And everything starts with a suitable substrate. As I already mentioned, that could be various material. It could be a lead frame, it could be a copper foil, a high current PCB, substrate with an embedded ceramic, and on that we do the die attach, typical silver sintering process of the die itself, application of the die, placement of the die, sintering of the die, if possible, and the application allows, it could be also a high conductive silver sintering glue, for instance. Soldering is not really an option because that does not really guarantee your position accuracy that you require, and also possible tilting of the die. And after the die attach, you go into the embedding process itself. And this is done by using the FR4 material, where you need different layers that you stack up. The first part is, or are layers which have cutouts for the components itself. They bring the height of the component. Then you have a full area prepreg material for the isolation and the copper foil as the base for the metallization. Doing that in a typical multi-layer lamination press, and followed by that you go into your typical PCB processing. So you create laser microvias to the embedded component, to the gate pad, to the source pad, and either mechanical or laser drills to the backside connection to the drain pad, and then go into a typical PCB process with the cleaning of the drill holes, the activation, the copper metallization, and the patterning. If you look into the different approaches, the most simplest thing that you could imagine is what we call prepackage, which is basically one semiconductor embedded using the PCB embedding technology, and with that creating just a single die package, which could be used then as SMD, as a typical SMD component to create a complete inverter structure or whatever you like to do with that. This could be done in that way, but also in an already electrical isolated way, where beside the silicon carbide die, you also do the embedding or the integration of your AMB substrate, which gives you the electrical isolation and also the good thermal path to the backside. You do see here an example of such an embedded prepackage with electrical isolation, where you have the silicon carbide die here, the ceramic here, and everything is embedded into the structure. And a little bit closer view just to the silicon carbide die, the silver sintered connection of the die, and the micro vias to the in this case the source pad of the semiconductor. This is an example which is already a couple of years old, but it still is a good example for what's possible with the silicon nitride inverter approach. What was done here was to use a pure organic approach using a thermal dielectric on the backside based on a thick copper substrate on which, again, the silicon carbide die was silver sintered to that substrate, and then embedded, and multiple routing layers were applied in order to create this half-bridge structure. And in this case, it was a silicon carbide inverter, which was capable of switching up to 100 kilowatt. And the picture pretty much illustrates what's possible beside just the pure embedding. You can already place DC link capacitors on top, shunt on top of that, and also high current connections. And if you had a look on that area here, this is just the illustration what we did. Just below these high current connections, you do see here the embedded components, the embedded silicon carbide dies, which are in the row here and here. And this pretty much nicely illustrates what's possible in that technology approach. This is a little bit newer one. This is from a German-funded project, which is called SiC Module, and was together with these partners here. And Schweizer did a lot of work in terms of the embedding, realized these half-bridge structures. And a good illustration here is also the goal here was really to create a six-phase inverter structure, which is very close to the motor, or which was assembled very close to motor, and also the possibility to shape these half-bridge structures in different ways just to fit here. And we also did beside or in parallel with the Schweizer approach and parallel path, where we looked into the integration again of ceramic substrate, and then in combination with a high current and a combination of a high current and logic board, which we then joined by a silver sintering technology again to create a similar structure. Just to firstly demonstrate also these possibility to join power and also logic parts into such an inverter structure. And this is some highlight project that I would like also to bring to your attention. This is some work that we do over the last 2 years almost for Mercedes-Benz together with Unimicron to assist Unimicron here. And the target here is really to create high current traction inverters like shown here in that picture provided by Mercedes. And the goal is really here to combine all these benefits that I tried to explain to you over the last minutes, apply a multi-level wiring structure over embedded MOSFETs, which gives you a lot of design flexibility, very thin, very flat modules that you then put onto your cooler location. And also the cost factor is very important here, because also with the embedded modules, you can achieve comparable cost if you compare that to other technologies at the same performance. The last thing that I would like to introduce is something that we did in a smaller German project together with the University in Magdeburg. And the idea here was not to focus on bare die embedding, but on already prepackaged GaN power transistors. And the basic idea was here to create different functional layers, like motherboard, the driver board, and the power module, and then to bring that together as a kind of a monolithic block that contains all this functionality and also the safety isolation, and provide with that also kind of a scalable configuration. This was done in the way that we created these function layers firstly. So the power part, the logic part with embedded SMD components, power part with embedded pre-packages. Then again, silver sintering joining technology to join the power part and the logic part. And as the last part, then to bring that module onto the power board with all the other additional components which are not able to embed because of their size. How did that look in the real world? This is just the example for the power and the driver part. So this is actually the power module with the assembled component, the driver module with the assembled module for the driving, the power modules using these GaN system pre-packages, cross-section of the logic part, and then joining that together. And you see here the joint cross-section of the power part and logic part, the large capacitor for the driver, and the silver sintering connections here. And finally, these power modules, which are quite small, are then soldered onto the motherboard, containing all the power connectors, and on the other side, all the assemblies which could not be embedded, and realizing the complete module to form these modular kind of power system approach. Okay, that brings me to my end, and I would like to summarize what I would try to bring you a little bit closer in the last minutes. So what we do see is that the embedding of power electronic components pretty much provides you a large benefit in terms of reliability and electrical performance. We do provide these direct copper connections between the die and all the surroundings, which bring you very short connection length, which pretty much reduce your parasitic inductance. And with that, you can improve your switching behavior, and the losses can be reduced significantly. It's very important that you understand what you do, not just having the idea on embedding, but also that you apply a proper thermal design and electrical design, also the modeling behind that, because this is really a key factor to realize a high performance system using that embedded approach. And I also try to bring to your attention that it's not just one possible way how you do realize your power package or module based on PCB embedding. This is really depending on the application at the end, which would fit best in terms of your demands on the thermal behavior, on the power density, and all these different factors which you need to take into account here. And also, lastly, we do have ideas and did that in a more research project way until now, how to create also kind of three-dimensional modular power electronics, which could be also a good idea to create very compact and highly integrated systems based on using the same established processes that I tried to describe a little bit more. And with that, I pretty much like to thank you for your attention, and I'm open for your questions in the chat. Thank you.